are, we found that an object can keep moving in 2D motion. We talked about that. Like if I throw a ball, once that ball leaves my hand, I am no longer pushing on it, but it keeps moving. Forces, okay, what a force is a push or a pull on an object. Okay? A force is a push or a pull on an object. There's things called contact forces versus, I believe the term is distance forces. But I don't get into the details of that. But the idea is I can physically push on something, right? I can push on something, or I can pull on something that I'm in direct contact with. But not all forces are like that. For example, if I drop a pen, there's a force acting on the pen. What is that force? But is gravity actually touching the pen? Okay, so not every force, girls, please stop talking. Not every force has to be in direct contact with one another. Okay, so a force is a push or a pull. A force, it is a vector quantity. And remember, vector commits crime with both direction and magnitude, both pieces. So it is a vector, so it has both a number and a direction associated with it. But when we talk about these, we use arrows to represent the directions, or we use arrows for the directions. We don't use positives and negatives for directions in forces. We draw these things called free body diagrams. A free body diagram, for example, is this. There's a bunch of them on the back side of your piece of paper. But it looks like that. And when we draw free body diagrams, it's a box. Pretty creative, I know. It's a box that has some arrows coming out of it, and we label the forces acting on that object. We define the directions of the forces because we need a number and a direction with the directions that the arrows point. So what we were saying was negative is now an arrow to the left. What we were saying is downwards is negative, we use an arrow for down. All of our forces, we use the number and a positive number, and then we address it with units. I'm sorry, with arrows. All forces, we use units of newtons for. And we simply abbreviate newtons with the letter N, capital N. Newtons. Any force. Doesn't matter which one, there's a list of 7 forces we're going to kind of introduce. All forces we measure with newtons after, of course, Sir Isaac Newton. A newton is a way we can measure things. We have scales that we can measure things in newtons. Ooh, that's heavy. Yeah, it's 8 newtons. Okay? To give you an idea what a newton is, I bought this apple out of a science catalog. This is 1 newton. Okay, I'll pass it around. It's foam. There's an elastic string. It's not a paddle ball, so don't try to pull it back. This string will break. But this is in this foam. Don't pick at it. Don't write on it. Just pass it around. This is about 1 newton. Okay, so 1 newton is about that much. It's not a lot. Depending upon how much you weigh, you might have 500 newtons. You might weigh 500 newtons to maybe 1,000 newtons, somewhere in that ballpark. Okay, again, really depends. But it's how we measure our forces is with newtons. So. So there's a bunch of forces that we have, and there's 7 of them that we are going to use. And I'm going to go through and I'm going to highlight the ones that have their own equations. So of these seven forces that I'm about to introduce, some of them have their own equations, some of them don't. If you want to be cool like me and use a highlighter, I have some. If you don't, I get it. It's hard to be like cool science teacher, I know. But of all the seven that we deal with, only 3 of them have their own equations that we can plug in for. Those 3, force of gravity, force of friction, and force of a spring, those are the only 3 forces that have their own equation to calculate. So if ever asked to solve for one of those 3 forces that I just highlighted, one option would be to use their own equation. If you have enough information, then you could use their own equation to solve for that value. Sometimes we do, sometimes we don't, but it's a good starting point. All 7 of these forces listed, and this is not an exhaustive list, this is just what we deal with. All 7 of these forces can be solved for using Newton's second law as well. So the 3 that I highlighted, you could try their own equation. If that fails, you can use Newton's second law to determine. If they aren't highlighted and you have to solve for that, you have to use Newton's second law. So Sir Isaac Newton, he's sometimes credited with 4 laws, but there's 3 about motion. One is Newton's universal law of gravitation. So when we go through and when I identify these forces, I personally always use a capital F to represent that as a force, and then I use a subscript. So subscripts are meant to be like below the line. I always use a subscript that goes with it to help identify the force it is. So the force of gravity, F of G, is also known, aka, as weight. So if you weigh 150 pounds, we measure in pounds, that's your force of gravity. That's the force that gravity is pulling down on you towards the center of the earth. We use pounds in the United States in everyday life. Realize in physics and science around the world, they don't use pounds, they use newtons. So if I were to say so-and-so weighs 500 newtons, I'm telling you the F of G. Okay, so we have weight. When we talk about free body diagrams and say, what forces are acting on this thing? And if you say force of gravity, like, I'm trying to think of an example where you aren't going to be right, you will be right. Force of gravity pulls on just about everything all the time. Force of gravity always pulls towards the center of the earth. So a lot of times people say down, yeah, but technically it's the center of the earth because the earth is round, and because it's round, it's always going to pull towards the center of the earth, no matter where on the earth you are. Always pulls toward the center. Now, Newton did not discover gravity. Gravity was known prior to Newton. Newton came up with a mathematical explanation of how we can determine or calculate what it is. And it's referred to as Newton's universal law of gravitation. And what it allows is it allows anyone to calculate any 2 objects that have mass, their gravitational pull towards one another. So most of the time what we deal with is we talk about what is my gravitational force that the earth is exerting downwards towards the center of. And it's not to the surface, it's to the center of the earth. And Newton was able to come up with a mathematical explanation, we call it a law because it's an explanation of what happens. And he found that any 2 objects that have mass, that there is an inverse squared relationship between the distance that they are apart. So the idea is the further apart something is, the less the attraction. But he did find that any two objects that have mass are physically attracted to one another. So the Earth is attracted to the moon, and the Earth is attracted to the sun, and we are attracted to the Earth, and we are technically attracted to the moon. Well, why don't we go flying off towards the moon? Because the pull towards the Earth is much greater. Okay, that's the idea. But it does pull on us, and we experience that, or we observe that pull from the moon with tides, right? We see the moon pulling on the ocean waters with tides. So Newton came up with that law about gravity. And it's something that can be applied to any location, which is really nice compared to what we talk about. We need to know some information about our location in order to do it. Normal force is abbreviated Fn. And that force exists when, and I'm going to put this in quote, when it's sitting on a surface. So anytime an object is, quote, sitting on a surface, there's a normal force. Now I put that in quotes because it's not always sitting. Example, I'm standing on the floor, but there's a normal force acting on it. What a normal force is it's a supporting force. It's a balancing force. Why are you not falling towards the ground right now? Why are you not accelerating towards the floor right now?
Normal force.
There's a normal force, but physically what's holding you up? Most of you, I think, are sitting on a chair, right? And that chair is pushing you upwards. It's holding you upwards. That upward force of the chair on you is what we can describe as a normal force. But it's only when an object is sitting on a surface. So if I take this, is this eraser sitting on a surface? No normal force, because it's not. When it's falling through the air, is it sitting on a surface? No normal force. Now there's a normal force. Now there's a normal force, okay? So whenever it's sitting on a surface, then there's a normal force. Force of friction is simply F of F, subscript F. And one thing to remember about friction, and we'll talk about it more when we get to it, it always opposes motion. It always opposes motion, which means it always acts in the opposite direction of the motion of the object. It always goes in the opposite direction. So an example of something that opposes motion would be my stool. Why did it stop? Friction slowed it down, okay? And there was enough friction that opposed it, like the stool was going this way, friction was going this way, that it eventually stopped the stool. There's also friction when I take my bowling ball and I roll my bowling ball across the floor. Is there a lot of friction? No, not a lot of friction. What was true about the speed of that bowling ball? It was relatively constant, right? Was it slowing down maybe a little bit? Perhaps. Was it speeding up a little bit? Perhaps, right? The floor is not perfectly flat, okay? So maybe it was going slightly downhill. It would have gained a little speed. Maybe it was going slightly uphill. It would have lost a little speed. Maybe, but there is a little bit of friction. Friction is always going to be in the opposite direction of that motion. Now we're going to talk about a couple different types of friction. There's static friction when an object's not moving. There's kinetic friction when objects are moving. We'll get to all that. The next force is kind of it's a very common one we use, and it's kind of a big category. Simply call it an applied force. An applied force is just a general way of saying that you're pushing or you're pulling on something. Something is applying some type of force. So if I'm pulling the cart, I'm applying a force to the cart in this direction. If I'm pushing on the cart, I'm applying a force in that direction. Okay? If I throw a baseball, as I'm throwing the baseball, I'm applying a force to that baseball. But once it leaves my hand, am I still applying a force to that baseball? No, right? Even though I got a cool Star Wars shirt on, I don't have Jedi mind powers like them. So once it leaves my hand, I can no longer keep pushing on it with the force. Okay? So once it leaves my hand, I'm not applying a force. So that's a very generic, like I threw, I pushed, I pulled. Okay? If I'm applying a force, if I'm doing something to some extent, we use applied force. A slight variation of applied force, it would be like tension. And when we talk about tension, we're talking like tension in a string, in a rope, in a chain. But depending upon what the tension is, we might call it applied force too. Because if I have a rope that's hooked up to like a chair, and I pull on the rope, is the tension moving the chair, or am I applying the force to the chair? And that's kind of semantics. Okay? The idea is there's a force that's going this way, whether it's the tension from the string, or we're looking at me that's applying a force which creates the tension. Okay, so sometimes we get into that and we can kind of call it an applied force. But sometimes, like if I were to take like a, I don't know, picture and hang it by a string, I don't know why I'd hang a picture by a string, but if I were to take a string and hang something up with it, there would be tension in it. Air resistance, we don't do a whole lot with air resistance. It's something we mention. It's not a calculation we do, it's called F of air. Air resistance is nothing more than a specialized type of friction. Friction is when two objects rub together, that's friction. Air resistance is when an object rubs together with air. Okay? It's just a type of friction. The reason we don't do much with calculations in air resistance is they're kind of complicated. Think about air resistance on your car. If you stick your hand out the window at 10 miles per hour, is there air resistance pushing on your arm? Yeah, right? Is it enough to be like, oh, maybe not, but you feel it. There's some air resistance. Now you're going down the highway at 55 and you stick your hand out the window, or 70 and you stick your hand out the window. Is there more or less or the same air resistance as there was at 10? Right, it's more. So the reason why air resistance gets kind of complicated in terms of calculation, it's a varied rate problem. And the idea is the faster you go, it increases the rate of air resistance, which in order to do a problem like that becomes calculus. Varied rate. So we don't do it. But we do talk about air resistance from the standpoint of, like, if I were to jump out of an airplane, we've oversimplified and like, I'm just going to free fall and my gravitational acceleration is going to be negative 9.8 meters per second squared. It's not really true. It's true for a moment, but as you start going faster and faster and faster towards the ground with your parachute, you're going to increase your air resistance. And then we hit something called terminal velocity, and we'll get into some of that stuff. So we don't do a lot with air resistance, but we talk some about air resistance. Force of a spring is F of S. It's also referred to as Hooke's law. It's a relationship between like a restorative force of a spring. If we have a spring and we stretch it, the distance we stretch that spring is going to pull that object. It's going to want to try to restore the spring back to where it was. Or if we compress the spring, same idea. Those three have their own equations, and I'll introduce those specific equations as we get to those three forces. All 7 of these can be solved for, determined, calculated, if we use Newton's second law of motion. So let's talk about Newton's laws of motion. Now I know Newton's laws of motion are not new. I know you talked about Newton's laws of motion in 9th grade. I know you even did some Newton's second law calculations in 9th grade. which is good. You have some background. I'm glad. So let's talk about Newton's first law. What is Newton's first law of motion?
Every action has a reaction to the opposing direction.
That's the third.
Okay.
Okay, that's the third. I'll get you started. An object. Okay. An object in motion tends to stay in motion unless acted upon by a outside force, or net external force is the way I'm going to. And there's a, instead of an object in motion, we could say an object at rest. Okay, good. So the way I write this is I write it as kind of a slash. So I say a body, we could say an object, but we often use the word body. A body at rest slash in motion tends to stay at rest slash in motion unless acted upon by a net external force. Okay, and I'm going to underline net external force. Now, there's a couple different ways. This is often referred to as the law of inertia. Inertia is a resistance to change. Generally speaking, things that have more mass have more inertia, and they're going to have a bigger resistance to change. So the way this can be read is a body at rest, we ignore the emotion, a body at rest tends to stay at rest, we ignore the emotion, at rest unless acted upon by net external force, or a body in motion tends to stay in motion unless acted upon by net external force. So, I don't know if you guys are old enough, or you guys, yeah, I don't know if you're old enough to have ever watched the Indiana Jones movie where there's a giant boulder rolling behind him and he like almost gets run over by this like 10-foot boulder. You've probably not seen the movie. Maybe you've seen the movie. I know there's, if you go to like Disney, there's Indiana Jones, I think it's the Temple of Doom, I think.
Oh, I went on it.
But there's a stage show that they have like a big boulder and they kind of like replicate it and all that stuff. Okay, that boulder is huge. And that boulder is in motion. Now Indiana Jones is like, he's run away. Why doesn't he just turn around and say, stop?
Because you won't be able to apply enough force to stop it.
Right, he can't exert enough external force and he goes smush, right? So that's the idea of net external force, or that's inertia, okay, that's inertia. Same idea with that resistance to change if it's at rest. If you were to try to get that giant boulder moving, it'd take a lot of effort, a lot of force to get that thing going. But once it gets going, it wants to keep going. We see some commercials, there used to be a commercial, I don't remember what it's for, I feel like it was some arthritis medicine, and they talked about a body at rest tends to stay in rest. But with this medicine, and they show like these older people getting up off their porch and being active. You guys ever see that commercial? You know what I'm talking about? I don't remember what it was for. But the idea is there. Okay? So that's inertia. Newton's second law is a mathematical law. And when we talk about this, we often see Newton's second law written like that. Oops, that's a little too far. Newton's second law is often just written as F net is equal to mass times acceleration. By definition, what net force means is it means the sum of all your forces. The sum of all your forces. So that right there is sigma, Greek letter in the alphabet, math terms used to represent summation, or the sum like equation or formula. So sigma F means the sum of all my forces is what sigma F means, the sum of all my forces. Now, sum of all my forces equal F net, which is equal mass times acceleration. That's Newton's second law, mathematical expression. When we sum up all of our forces, Again, we talk way up at the top. I don't use positive and negatives, I use arrows to represent directions. So if I'm going to sum up all my forces for this, it's called a free body diagram, there's some on the back we'll get to. This is a free body diagram. Just like in 2D motion, we keep our x's separate from our y's. The stuff in our x columns and our x directions we keep separate from our stuff in our y columns. X's separate from their y's. So when I sum up all my forces, we sum up all the forces in the x direction, independent from the sum of all my forces in the y direction. We don't have positive and negatives. This is positive, 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 positive. We talk about the magnitude or how big they are. Their directions come from the arrows. But when I sum these up, the way I do it, and I'll say this a lot, when we sum up our forces in the x direction, what we do is we add all of the green forces. But this is in the left direction, so I add my rights, all the forces going to the right I add, and I subtract my lefts. Now we could have one force to the right, we'd add one. We could have three forces to the right, we would add all three of those. So we add our rights, and we subtract what I refer to as our lefts. Okay, I don't think that's official terms, but we add our rights and we subtract our lefts. We add the forces to the right. We subtract our forces to the left. Same idea when we talk about the y direction, which we do independent from our x direction. We add our ups and we subtract your downs. So all the forces that are going upwards, we add. Sometimes there's one, sometimes there's two, sometimes there's three. And we subtract our downs. Sometimes there's one, sometimes there's two, sometimes there's three. A lot of times there's one, but we add them. If there's however many there are, we add. Now, if we go through and we use Newton's second law and we say, hey, if F net is equal to 0, so if this number is 0, well, in order to determine this, we had to take this times this. One of these two numbers would have to be 0 in order for my F net to be 0, right? Mathematically. 0 is equal to something times something. One of those somethings has to be a 0. When we talk about mass, we'll get to in the bottom. Mass is anything that takes up space, is made up of atoms, or matter, has matter. Then it has mass. So everything has mass. The air around us has mass. Almost everything has mass. Photons of light don't have mass. Almost everything has mass. Okay? So if just about everything in the world has mass, and if our F net is 0, well, this number is not 0, so therefore our acceleration must be 0. Now, when we talked about acceleration, I talked about what causes acceleration. I threw that out there just to kind of plant that seed. When we talk about an object accelerates when the forces are unbalanced. So if the sum of all your forces add up to 0, and when we sum up our forces, that means I got to add my rights, I subtract my lefts. If this minus this is equal to 0, my acceleration is 0. And if my acceleration is 0, what does that tell me about my velocity?
Constant.
It's constant, right? So my velocity is constant, which means my forces are balanced. I have balanced forces. That means in the x direction, my rights minus my lefts are balanced, they equal 0. In my y direction, my ups minus my downs add up to 0, means my forces are balanced. Now, if one of these statements is true in this line, every statement in that line is true. So your velocity is constant, that means your forces are balanced, your F net is 0, your acceleration is 0. Now, the inverse, or the opposite of all this is true, so if your F net does not equal 0, that means your acceleration does not equal 0. Right, so I made that a little bigger. if your F net isn't 0, it's 1, it's 2, it's 0.867, that's not 0, any number except 0, then your acceleration is going to have some non-zero value. And if your acceleration is not 0, that means your velocity is changing. That's the definition of an acceleration. And the reason why that happens is because your forces are unbalanced. You have unbalanced forces. No acceleration means constant velocity. People often see acceleration equal to 0, and they automatically assume that means velocity is 0. That's not true. This is an example of no acceleration. Right? My velocity is not changing. I'm not moving. My acceleration is 0. My bowling ball is pretty close to constant velocity. The velocity of that bowling ball is relatively constant. Let's make the assumption it is constant. If your velocity is constant, that means my acceleration is 0, which means my forces are balanced, which means my F net is 0. No acceleration does not mean, always, no velocity. An object can be moving, but not accelerating, just constant velocity. Cruise control down the highway, right? Straight line, cruise control on, constant velocity. Newton's third law. Newton's third law is for every action there is an equal, there is an equal and opposite reaction. For every action, there is an equal and opposite reaction. Now, when we talk about action or reaction, what we're really saying is forces come in pairs. They come in balanced pairs. If I were to go home, and if I would have gotten an email from my son's grade school teacher, and the email says, your son hit someone on the playground today, and I go home and say, hey, I got an email from your teacher, says you hit someone on the playground, and if they say, yeah, but Newton's law says that he punched me, therefore I get to punch him back, I'd be that a boy, but that's not how that actually works, okay? Attaboy for not punching a kid, just for clarify. It's because you know physics, you know Newton's third law, not because you punched a kid. Parenting clarification there. Okay. So we sometimes try to use it, but it's not actually how it is. But what this is saying is we come in equal action pairs. So if I were to punch someone, I'm not sure why I would punch someone, but let's just say I punched someone for some reason, right in the face. I'm not sure why I punched them in the face, but I did. Okay, let's be more realistic. Someone punched me in the face. That's probably more likely what would happen because they are mad at me for some reason because I was mean to them or something. I don't know. So let's say I get punched in the face, okay? They exert a force on my face of some value in newtons, 50 newtons. I don't care, it doesn't matter. Ow, 50 newtons. Ugh. I'm gonna fall on the ground and I'm gonna be like, oh, that really hurt. But they're gonna be shaking their hand, they're gonna be like, because I pushed back with my face 50 newtons equally. And be like, take that, fist. My face hurts, but I pushed back, equal and opposite. Okay? Reaction pairs. True story. I was driving home on Saturday night and I hit a deer. Okay? I hit the deer with the car. The car exerted a force on the deer. Okay? The deer exerted an equal and opposite force, a very pricey, expensive force, on my car. but they were equal and opposite, which caused the change in velocity, which caused the change in speed. Okay, and we could get to like down to really small things like, hey, a bug went splat on my windshield. The bug actually slowed my car down just a little tiny bit because it exerted a backwards force. Okay, now we're talking about like immeasurable kind of stuff, but that's that idea. Newton's third law, equal and opposite forces. All right, let's turn this over and let's take a quick look at one of these problems. So on the back of these are called free body diagrams. And free body diagrams are pictures, generally boxes, that have forces with arrows, and the arrows point in the direction that the force goes. They have ideally a number value written next to it, and their rough approximations of length are scaled somewhat appropriately. So what I'm trying to say is if this force is 5 newtons and is that big, this and this one's 3, the 5 should be longer than the 3, right? I'm not going to get a ruler out and measure them. Oh look, the 5 was there. Oh look, the 3 was much bigger, right? So they should be a little bit longer if it's bigger to show rough scales. Again, I'm not going to ask for perfection in scales. So we go through, we draw a picture. We label all of our forces on it with the direction that the forces are acting. And then based upon that, we can go through and we can apply Newton's second law to determine what the net force acting on each object is. Now, I should have said this earlier. Newton's second law, the way I write Newton's second law has 3 parts to it. The sum of all my forces equals F net, which is also equal to M times A. So just remember in math, if A is equal to B and B is equal to C, then all 3 of these are equal to one another, right? So we could say that A is equal to B is equal to C, or we could say A is equal to B, or we could say A is equal to C, or any combination. So the reason why I have 3 parts to it is based upon what we want or what we know. Kind of depends upon which 2 of the 3 pieces we're going to use. So when we go through and we try to determine the net force acting upon the object, what I'm really asking you to do is find the sum of all your forces in the x direction, which is equal to the F net in the x direction, which is equal to mass times acceleration in the x direction. And I need to do this for my x forces independently from my y forces. Now I'm going to do it this time. We're going to get, so we don't do a lot of this in this level of detail at this simplistic of a problem, but we're introducing it, so I'm going to show you it. We'll quickly progress from here. But this step is something I encourage you to use when we do our calculations. So I'm trying to solve for the F net. That's what I'm trying to figure out. There's nothing in here mentioned about mass or acceleration, so I'm not going to be using that part, and I'm really going to be using the first and second part of my equation. Now the sum of all my forces in the x direction, well, when I sum up all my forces in the x direction, I need to add your rights and subtract your lefts. So if I look at my free body diagram, my rights are the forces going to the right, my lefts are the forces going to the left. And I really encourage you to do this step. People get lazy and they say, I don't need to do that. I really encourage you to do it because I think it's worth the extra 5 seconds. That when we go through and we sum up all my forces in the x direction, we label them by name. So if I'm going to add my rights, I put a plus sign, all of my forces by name that are going to the right. And in this case, I'm only looking at part A right now. I add all my forces going to the right. Then I subtract all of my forces going to the left, and I'm going to call it just F of F, because that's what I call force of friction. And those are the only forces in my x direction, and then I can set that equal to F net in the x direction, which is what we're trying to solve for. Now I plug values in, and I'm going to say plus 5, because that's my applied force, minus, and I look, oh, my force of friction is 5, and that's equal to F net in the x direction, which is equal to 0 newtons. Sorry, newtons. Voice crack. It happens. Okay, let me quickly go through the y direction. We do the same thing in the y direction. Sum of all my forces in the y direction is equal to my F net in the y direction, which is equal to mass times acceleration in the y direction. I don't know anything about mass or acceleration. According to Newton's second law, I add my ups and I subtract my downs. So I look at my free body diagram and I add all of my forces that are going up. I have a normal force. I subtract all my forces going down. I have a force of gravity. And that's equal to F net in the y. I add my values to my equation to quickly determine that my F net in the y direction is 0. Now, when we talk about F net, I need about 30 seconds. When we talk about F net, I'm not talking about the F net in the x, I'm not talking about F net in the y, I'm saying we have to do both, and then we have to like smash them back together, really. Conveniently, net force in the x is 0, my F net in the y was 0, so overall, my F net is 0. Which means, string of statements, if my F net is 0, my acceleration is 0, my velocity is constant, all of my forces were balanced. Now we can go in reverse, we can look at that, we'll start doing that. Hey look, my forces are balanced, right? 5, 5, 3, 3, which means my F net's 0. Okay? So that's where we'll pick up on Monday. Have a wonderful 4-day weekend, everyone.